Hello students, I am Azizi, Professor Electronics. In our previous session, we have studied that what is an alphanumeric LCD, and we have also studied the different function bits to initialize the LCD, and we have developed a circuit to interface the LCD with the microcontroller, that is 88C51. So first we'll discuss about the circuit that we have developed on Proteus software, and then we will write a program to display alphanumeric data on LCD. So let's start our today's session. Here we can find the circuit that we have developed in our previous session. We have connected an alphanumeric LCD, that is LM044L, and we will use this LCD to simulate HD44780 Hitachi LCD. And we have connected the data pins of the LCD, that is from D0 to D7 on port 0, that is from port 0.0 to port 0.7, and we will develop a program for 8-bit interface for this LCD, because to interface this LCD on 4-bit interface is a little bit complex as compared to the 8-bit interface. So in this session we'll write a program for 8-bit interface, and here we can find 3 control signals, that is RS, RW and enable, and we have connected these control signals on port 2.3, port 2.4 and port 2.5. Now first we'll learn that how to display a character on different rows and columns of this LCD. So let's start writing our first program for the alphanumeric LCD. As we have discussed in our previous session that the function bits for HD44780 LCD, that is to clear display, cursor home, entry mode set, display on off control, cursor display shift, function set, set CG RAM address, set DD RAM address, and here we have written the equivalent data numbers to perform the initialization task for this LCD, that is HD44780, and here we can find to perform the clear display function we have written the number 1 in binary, and also we can write this number in decimal as 1, and to perform the cursor home function we have written the equivalent data, that is 2. Similarly we have written the equivalent data for entry mode set, that is 6, and similarly for display on off control we have written the data, that is 00001100 in binary, and to execute the cursor display shift function we have written the equivalent data, that is 000110100 in binary, and for the function set we have written the equivalent data, that is 00111 and 000 in binary, and we can check from this data that what functions will be performed if we will use these commands. That is, if we will move the number, that is 01 to the LCD port, it means that we want to clear the display, and if we will move the number, that is 02 to the LCD port, it means that cursor home. And here we can find for entry mode set we have set the value of DB2 as 1, and here we have 2 control bits, that is 1 over D and S. Here we can find the value of 1 over D is 1 and S is 0. It means that we will use the function that is increment cursor position, and the status of the S bit is 0, it means no display shift. And here for display on off control we have written the number, that is 0001100. For display on off control function the value of DB3 bit must be 1, and here we have 3 bits, that is DB2 for D, DB1 for C and DB0 for S, and here we have set the value of DB3 as 1 to execute the function of display on off control, and the next bit, that is D, is 1, and here we can find if the status of the D will be 1 then display will be on, and to display any character on the LCD it is required to set the value of D as 1, and for cursor display shift function we have written the equivalent data, that is 0001100. It means that we have set the value of DB4 as 1, and here we have 2 functions, that is S oblique C and R oblique L. In this case DB1 and DB0 are don't care, and here we can see we have set the value of S oblique C as 0. It means if the value of S oblique C will be 0 then move cursor function will be performed, and we have set the value of R oblique 1 as 1, and here we can find if the value of R oblique 1 will be 1 then shift right function will be performed, and for function set we have written the equivalent data, that is 0011100. In this case we have set the value of DB5 as 1, and here we have 3 function bits, that is DL, N and F, and in this function DB0 and DB1 are also don't care, and here we can find we have set the value, that is DB5 as 1, and the next 2 bits are also 1. It means we have set the status of DL as 1, and here we can see if the status of DL will be 1, it means that we want to interface our LCD with 8-bit interface. But if the status of the DL will be 0, it means that we want to interface this LCD on 4 bits. After DL bit we have next bit, that is N, and we have set the value of N as 1, and here we can find if the status of this bit, that is N, will be 1, it means 2-line interface, and we have set the value of F bit as 0, and here we can find if the status of this bit, that is F bit, will be 0, then the character will be made using 5 cross 8 dots. So here we have set the value of F as 0, And also in this function, the value of db0 and db1 are don't care. So here we have composed the equivalent data to initialize this LCD for our program. And now we'll use this data in our program. And here we can find the program, that is manual counter program, that we have written in our previous session. First we'll close this project and we'll develop a new project. So we'll go for the project. Okay, close project. And we'll go for the project, new microvision project. And here we will develop a new folder to write our new program. And we'll assign the name to this folder, that is LCD programs. And here we'll assign the name to our project, that is LCD project 1. So we'll write that is LCD underscore project underscore 1. Okay, save. And now we'll select the microcontroller, that is 89C51. Okay. No. Now we will go to the target 1, right click, option for target 1. And here we will write the value of the crystal oscillator that we are using in our project. So we are using a 12 MHz crystal oscillator. So we'll write 12.0 here. Now we'll go to the output and we'll select this checkbox, that is create hex file. Okay. In source group 1, right click, add new item to source group 1. And here we'll select ASM file. And here we'll assign the name to the file, that is LCD project 1. So we'll write that is LCD underscore project underscore 1. Okay, add. And now we'll start writing our LCD project. So first we'll assign some comments. So here we have written the name of our project, that is my first LCD project, as comments. And we have added some more information regarding our project, that is we are working on HD44780 LCD and we are using 8-bit interface. And now we'll copy all these numbers that we have composed to initialize our LCD. And now we'll add constants assignment in our program. And here we'll add the first constant, that is clear display. So we'll write that is clear disp, and we will write that is EQU. And here we will write the equivalent number for clear display function. And here we will assign the number to clear display function, Control V. So here we have written the equivalent number for clear display function. Now we'll write all other functions. Cursor home, EQU, and the equivalent binary number, that is 2. And now we will write the third function, EQU, and the equivalent binary number. Here we have written all the initialization functions and their equivalent numbers in binary in our constant assignments. So here we will close the section of our constant assignments and we will add more constants as and when required in our program. And now we'll write the ports assignments. As we have connected all 8 bits of the LCD with the port 0, so we'll assign the name, that is LCD port, to the port 0. And here we can find we have connected 3 control signals, that is RS, RW and enable, with port 2.3, port 2.4 and port 2.5. We'll also assign the names to these bits in our program. And here we will assign the name to the port 0, that is LCD port. So here we will write that is LCD underscore PRT EQU port 0. And now we'll write the bits assignments. And here we'll assign the name to port 2.3 as RS. So here we will write that is RS. And we'll write that is bit. And here we'll write port 2.3. And we'll assign the name to port 2.4 as RW. So we'll write that is RW. That is bit. Port 2.4. And we'll assign the name, that is enable, to the port 2.5. So we'll write that is EN. And here we can check we have assigned the label, that is RS, to port 2.3. RW to port 2.4 and enable to port 2.5. And here we have assigned the name to these ports, that is port 2.3, port 2.4 and port 2.5. And now we will write the directives for our program. And here we will direct our program to start writing the first instruction from the 00H location, which is the reset vector for the microcontroller. So here we will write that is originate. And now we'll write the first instruction for our program. And here we will write that is jump ini underscore r, that is initialization routine. After writing this command, we will originate another address, that is org 0030H. It means we will start writing our initialization routine from 30H. So here we will write the initialization routine, and here we will write that is inir using colon. And here in initialization routine, we'll set the value of port 0 as 0. So we'll use the command that is move port 0, comma hash 00H. And here in initialization routine, we'll clear the status of RS and RW bits. So we'll write that is clear RS clear RW, and we'll set the status of EN, and here we will write that is set bit EN. And now we will write the initialization delay for the LCD. As we have discussed in our previous session that this LCD requires at least 10 milliseconds after VCC rises to 4.5 volt to initialize its internal functions. So we will write a 20 millisecond delay in our program before sending any command to the LCD. And here we will write a 20 millisecond delay routine here in our program, and here we will assign the label to the delay, that is LCD initialization delay. So here we will write that is LCD underscore ini underscore DLY using colon. Now we will calculate the register values to develop the delay of 20 millisecond. As we are using a 12 MHz crystal for our project, it means the machine cycle will be 1 microsecond, and we will use the instruction that is decrement jump not 0 in this delay routine, which takes 2 machine cycle. It means that the instruction will take 2 microseconds. So let's see how can we calculate the value of the registers to develop this delay of 20 millisecond. If we will use a single register to develop this delay, it means that 256 multiplied by 2 microseconds It means that by using a single register, we can have the delay that is 0.512 milliseconds, but we require the delay of 20 milliseconds. So let's see how we can calculate this delay. As we know that 20 millisecond means 20,000 microseconds. So here we will write that is 20,000 microseconds. And now we'll divide this number by 256, that is the maximum value for the 8-bit number. So first we'll divide this number by 256. And here we have the number that is 78.125, and we will use the instruction that is decrement jump not 0 in this delay routine. It means it will take 2 microseconds. So we'll divide this number by 2. And here we have the final result, that is 39.0625. It means that we will use 2 registers to develop this delay, and we will assign the number that is 255 to the first register, and we will assign the value that is 39 to the second register. So let's calculate the delay of 20 millisecond by using these 2 numbers. Now first we'll multiply 256 by 39, and here we have the result, that is 9984, and we'll multiply this number by 2 microseconds. And here we can find the result, that is 0.019968 seconds. It means 19.968 milliseconds. So to get the delay of 20 millisecond, we'll use 2 registers, and we will initialize the first register to 255 and the second register to 39. And here we will use 2 registers, that is R0 and R1, to develop this delay from the register bank. So here we'll use that is move R0, comma hash 39, and we'll use move R1, comma hash 255, And now we'll use the instruction that is decrement jump not 0. So here we will write that is decrement jump not 0 R1 comma $. It means that first decrement the value of R1 and compare the value of R1 with 0. If the value of R1 is not 0, then jump to the same line. The $sign in the instruction that is decrement jump not 0 means jump to the same line. But if the value of R1 will be 0, then our program will come to the next line, and here we will write that is decrement jump not 0 R0 comma, and here we will write the name of the subroutine to which our program will jump if the value of R0 will not be 0. So here we will write the name that is go back, and here we will write the label that is go back after this line. Using colon, and here we will close the initialization delay routine. And now we can check the working of this subroutine. That is, here on this line we are initializing the value of R0 as 39, and here we are initializing the value of R1 as 255, and here we have used an instruction that is decrement jump not 0 R1 $. It means that our program will jump to the same line for 256 times, but if the value of R1 will be 0, then our program will come to the next line and it will decrement the value of R0 and will check if the value of R0 is 0. It will jump to the subroutine that is go back, and it will move the value that is 255 to R1 again, and this delay and delay loop will be executed for 256 times multiplied by 39 multiplied by 2 microsecond, and the total time for this delay and delay routine will be approximately 20 millisecond as we have calculated. And now we will write the initialization routine for the LCD, and here we will move the first command to the LCD port, that is clear display. So here we will write that is move LCD PRT, that is port 0, comma hash. We will copy this variable from here, clear disp, and we will paste it here, Control V. It means that we have moved the code for clear display on LCD port, and now we'll call a delay of 1.52 millisecond, and here we can find two functions, that is clear display and cursor home, require 1.52 milliseconds to execute. The other commands, that is entry mode set, display on off control, cursor display shift, function set, all these functions require a time of 37 microseconds to execute, and here we will call a delay of 1.52 milliseconds required to execute this function. So here we will write that is call, that is ms_dly, that is the delay of 1.52 milliseconds. So here we will write that is milliseconds delay, and here we can check we have set the status of the enable bit in initialization routine. So now we'll clear the status of the enable bit, that is CLR EN, and here we'll call the delay, that is ms delay once again. So here we will write that is call ms_dly, and now we'll set the value of EN bit as 1. So here we will write that is set bit EN. So here we have written the command that is clear display to the LCD, and now we'll write the second command, that is move cursor to home. So we'll write that is move LCD PRT, comma hash. We'll copy this variable from here, that is cursor home, and we will paste it here, Control V. And after moving this command to the port, we'll call the delay, that is ms delay once again. So here we will write that is call ms_dly, and here we will clear the status of enable bit. So here we will write that is CLR EN. We'll call the ms delay once again, and after calling this delay, we'll set the status of the enable pin as 1. So here we will write that is set bit EN, And now we will move the code for entry mode set to the LCD port. So here we will write that is move LCD PRT comma hash. We will copy this variable from here and we will paste it here. As we have seen, all the initialization commands other than clear disk and cursor home requires only 37 microseconds to execute the function. So here we will use another delay subroutine, that is 50 microsecond delay routine. So here we will write that is call USDLY and we'll assign the comment. After executing this 50 microsecond delay, we'll clear the status of the enable bit. So here we will write that is clear EN, and here we will call the microsecond delay once again. So here we will write that is call USDLY. After calling this microsecond delay, we'll set the status of the EN bit as 1. So here we will write that is set bit EN. In the same way, we can implement the other three commands, that is display on off control, cursor display shift, and function set. And here we have completed the LCD initialization routine, and now we will write the two delays, that is millisecond delay and the microsecond delay. So here we will write the delays, and here we will write the name, that is MS delay. So we will write that is MS DLY using colon. If you will use a single register to develop this delay, then we will have a delay of 0.152 milliseconds. But to have the delay of 2 milliseconds, we require two registers. So here we will write that is move R0 comma hash 4, and we will write that is move R1 comma hash 255, and now we will write that is decrement jump not 0 R1 comma $, and here we will write that is decrement jump not 0 R0 comma, and here we will assign a label, that is MS delay 1. So we will write that is MS DLY underscore 1, and here after this line we will assign the label, that is MS delay 1. And if the value of R0 will be 0 as a result of the above instruction, that is decrement jump not 0, then our program will come to the next line and it will get returned from the subroutine. So here we will write that is return. Here we have completed the 2 millisecond delay subroutine, and now we'll write the delay routine for 50 microseconds, and here we'll assign the label, that is US delay using colon. And here we'll move the number, that is 25, to the R0. So we'll write that is move R0 comma hash 25, and here we'll write that is decrement jump not 0 R0 comma $. It means that the delay time will be 25 multiplied by 2 microseconds equals to 50 microseconds, and if the value of the R0 will be 0 as a result of decrement jump not 0 instruction, then our program will come to the next line and it will get returned from the subroutine. So here we will write that is return. So here we have completed the routine of 50 microseconds. As we have written the routine for 20 millisecond delay for the LCD initialization, and we have written the initialization routine for LCD, now we will write the main routine. So here we will write the main routine, and here we will write that is main using colon, and in the main routine we will just write a character on the first row and first column of the LCD, and we'll see that how to write the same character on different row and different column of the LCD. And here we can find the starting address of the rows, that is 80H for row 1, C0 for row 2, 94H for row 3, and D4H for row 4. So let's check how can we write our first character on this LCD. So here in main routine we will call two subroutines. The first routine will select the position to print the character, and the second routine will print the character. So here we will call two subroutines, that is call go position and call prnt underscore chr, and after executing these two subroutines our program will jump back to the main. So here we'll write that is jump main, and here after this instruction we'll write the subroutine that is go position, and here we will write the name of the subroutine that is go position. So we will write that is go pose using colon, and here in the subroutine we'll move the address of first row and first column to the LCD port. So here we will write that is move LCD PRT comma hash ATH. As we have seen, the address of the first row and the first column of the LCD is ATH, and after moving this value to the LCD port we will call the delay of millisecond. So here we will write that is call MSDLY, and now we'll clear the status of the enable bit. So we'll write that is CLR EN, and we'll call the millisecond delay once again. So we'll write that is call MSDLY, and here we'll set the status of the enable bit. So we'll write that is set bit EN, and here we have completed our go position subroutine. So after executing this instruction that is set bit EN, our program will get return from the subroutine. So here we will write that is return, and now we will write the second subroutine that is print character, and here we will write the routine that is print character. So we'll write that is prnt underscore chr using colon. Here we can check in initialization routine we have written the clear RS bit, but to write any character on the LCD first we have to set this bit. So we will write that is set bit RS, and after setting the status of the RS bit we'll move the value of the character on LCD port. So here we will write that is move LCD PRT comma A. So here we have assigned the character A to the LCD port as text, and now we will call the millisecond delay that is call MSDLY, and now we'll clear the status of the enable bit. So we'll write that is clear EN, and again we'll call the delay of millisecond, and now we'll set the status of the enable bit as 1, that is set bit EN, and we'll call millisecond delay once again, that is call MSDLY, and after executing this millisecond delay we'll clear the status of the RS pin. So we'll write that is clear RS, and here we have completed our print character routine. And before leaving the subroutine we'll write the return instruction on the next line. So here we'll write that is return. So here we have completed our two subroutines, that is go position and print character. Now we'll compile our program and we'll observe the result of our program on Proteus simulator. Here we can check 0 errors and 1 warning, and the warning is missing end statement. So here we will write that is end, and now we will compile our program once again. 0 error, 0 warnings, and now we will download the new hex file to the microcontroller. Here in LCD programs folder, in objects, here we have the hex file that is LCD project 1. OK, and now we will run the simulation. Here we can check no characters displayed on first row and first column. It means there is some mistake in our program. Let's check what is the error in our program. And here we can check we have assigned the character that is A to the LCD port. But to move this character to the LCD port we have to use a hash character before A. So here we will write the hash, and now we'll compile our program once again, and now we'll run the simulation once again, and here we can find the character A is printed on the first row and first column of the LCD. In this session we have learned that how to initialize the LCD, that is HD44780 LCD, and we have learned that how to print a character on first row and first column of the LCD. In our next section we will explore our program in more details, and we'll check that how to print the same character on different row and different column of this LCD. Thanks for watching this semi-language programming course. We hope that you find this course very helpful to learn semi-language programming. If you feel that this course contributes and enhances your embedded system design knowledge, then go ahead and hit like, share and subscribe buttons, and do not forget to press bell icon to stay updated with every new upcoming video from Electro Educators as soon as it goes up. Electro Educators also offers technical consultancy in following fields. For assistance regarding technical problems, projects and any consultancy, feel free to reach out at our email address electroeducators@gmail.com. Okay, see you in next lecture.